Hello, hello, everyone. Happy Sunday. We ready to get our chemistry on? Yeah. I see that a lot of people are joining on now. So I wanted to talk to you guys before we even begin. So what I am planning on doing, as you really know, we're doing these Sunday sessions every single time, and I'm doing this as a thank you. As many of you guys may know, I am a tutor. So this is, my job, and this is what I do for a living. So I typically charge between $40 to $60 an hour for tutoring, but because I'm so thankful that you guys are subscribed and really just thankful and grateful for you guys being subscribers, I'm doing this for free as a thank you. So something else I wanted to talk to you guys about was I know finals are going to be approaching very soon, and I know finals tend to be chaos. So as a way to help you guys, I wanted to do an 8-hour live session for your final, but that is if you guys could help me get to 10,000 subscribers. Okay, so I would, so sweet, Jamie, thank you. So if you guys help me get to 10,000 subscribers, so share with your chemistry class, your teachers, your friends, anybody you know that can benefit from this. Help me get to that 10,000 and I will do an 8-hour live tutoring session before your final. That's going to help. So I'm going to be there studying with you. If you feel like, for you guys not to cram and just to feel like you're ready for your final. Okay. Priscilla says game on. Awesome. Happy to hear. Megan says we'll spread the word. Thank you guys. Awesome. So yeah, just wanted to let you guys know that. All right, let's kick it off with electron configuration. So let's jump to this. Give me 1 second. Tiny technical difficulty. 1 second. Sorry, guys. Okay. Sorry, guys. That was strange. I just wasn't able to share my screen for some reason, but we're good. We're back on. So back to joining, talking about electron configurations. Okay. So electron configurations. As you can tell, there are different types of energy levels, or we also refer to them as shells. So electron configuration is really just talking about where in the world those electrons are, or like where are the overall orbitals that they share. So I want you to kind of just think of electron configuration is a way for us to know where electrons exist. So what orbital? Okay, there are specific types. As you can tell here, we have 4 different types of shells, the S, P, and D, and F shells. And I listed it according to the strength or how much energy each one has. So our S orbital has the least amount of energy, then followed by P, D, and F. Next, there's also different types of subshells. So our S orbital, since it has the least amount of energy, will only have 1 subshell. So how this will, you actually might have already seen this, how our electrons will exist. They're going to look just like that. So they're always going to be, this is called opposite spin. Really, this is just a way for us to draw out the electrons. They're going to repel each other. That's why they're not going the same way. I would never draw electrons this way. Okay, just note that. Another thing that I will be going over is something known as Hund's rule, but we'll get to that. Now going on to the p orbitals, there are 3 different subshells. So in this case, we will have, this is actually going to be Hund's rule. The way we're going to fill these electrons or these subshells is going to be one at a time. So electrons don't like each other, okay? They repel each other. I want you to think of them kind of like antisocial. So they don't want to be in the same room or in the same subshell as each other. So for p orbitals, this is going to be filling up one subshell first. So 1, 2, 3, then coming back and filling up the rest only if they have to. So, and something else I wanted to mention, for s orbitals, there can be 2 electrons per every subshell. P orbitals, or our p shells, will then have 6 possible electrons because there are 2 electrons per every 1 subshell. And then now for our D, we actually have 5 different subshells, and I'll draw them out again. This is Hund's rule. Whenever electrons, pretty much how we're drawing electrons, we never want to place them, like we never want to do this. Actually, we never want to do this specifically where we're just, you know, filling up those subshells. No, you want to do that one at a time. For our d orbitals, then we will have a total of 10 electrons. And then next for our f orbital, there are 7 subshells. It's really rare if you guys actually have to do the f subshell or f block, but we'll get to that either way. And then we actually would have 14 electrons. And let me just fill those in as to how you actually will see them. All right. So another thing that you might have seen is just the overall shapes of the different subshells. So for our S shell, it's just one subshell, right? We only have one. So electrons can exist within this shell, and then they really don't like to be next to each other, but that's a possibility. So that's where this would have just been one subshell. Rather, P can have 3 different subshells because it could look something like this, where it's PX, PY, and PZ. You guys will later get onto like more of the technicality of whether it's in PX, PY, or PZ. Don't worry about that too much right now. But that's just showing you that electrons could either be here or they can be on the opposite side. There's really no way to tell, sadly. Electrons are just, they have a mind of their own. So electron configuration is just like an idea of where electrons can exist. All right, and let's see so far, I know. Okay. Cool. All right, and then let's see. Let's continue on to actually how to do this. So there are different types of blocks that you'll see for your periodic table. For this first one, we'll have the S block. So this, just exactly how you see it on the screen, this is what it's going to be, the S block. You're also going to have the P block. The D are your transitional metals, and then F at the very, very end. Okay, so this is definitely something to note. We do go based on the rows. So like this first row would have been 1S, and then our second row would have been 2S, but then we would have continued. So continuing on, then we would have gone to 2P, and we'll keep going. Then we would have gone to 3S, continuing on to 3P, but there's a difference here whenever we get to our d orbitals. So we would get to 4s, but something to remember, for your d orbitals, it's always one less than the row that it's actually in. So in our case, we see that even though this is in the 4th row, it's actually going to be 3d. So all of your d values, so the d values will always be, I want you to subtract really, and you've seen this probably as n minus 1. N really is just referring to the different rows that you're in. So like this is n4, n equals 3. I want you really just to think of n is just the row that it's in. So in our case, this is n minus 1. So since this is in the 4th row, it's actually going to be 3. Same thing here. Since this is in the 5th row, it's actually going to be 4, and so on. There's something else to note. For your F block, this is actually going to be n minus 2. So I know it doesn't show it here, but this F block is actually right in between, or in the 6th row. So it's typically in the 6th row, this F block, the 4F, and then from there you would have subtracted by 2 to get that 4F. Okay, so D blocks, you always subtract 1 from the actual row that it's in, and then F blocks, you always subtract 2 from the actual row that it's in. Okay, moving on. There we go. Let's try some. So this is what it would typically look like. I'm going to start off with the actual expanded version. So you're going to have 2 specific versions of Electron configuration. You're going to have a shorthand or an abbreviated method, which we use the noble gas, and I'll explain that. And the other one is the longhand or the expanded form. So I'm going to start with the expanded form or the standard form. I've heard it so many different ways. Let's say if we started with oxygen. All right, so I'm going to kind of come closer here. This is oxygen. And I'm going to just start off with, and this actually cut off, I realized. Helium would have been, oh no, I think this actually cut off. Let me see if I can, and this cut off. Okay, work with me, guys. Helium would have been here. Goodness, okay. So this would have been, and you know what, better yet, let me just go back to this method. This is going to be easier. For oxygen, oxygen would have been right here. There we go. All right, this is just going to be nicer. So oxygen would have been right here where I drew it. So how I'm going to do this is I'm going to start off with 1s, because that's what we always begin with. So 1s right here. I'm just doing oxygen. Okay. 1s, and then it's going to continue going to 1s2 because we filled that subshell. Then I'm going to continue on, and I'm now going to get to 2s. I then use up all of this, meaning there's 1, 2 electrons, right? 1, 2 electrons. So that would have been 2s2. Now I'm going to continue, and I'm trying to just stop at this oxygen that we see right here. So then this would have been 2p, and then now we're going to count to how many oxygen or how many electrons we have to get to oxygen. So this would have been 1, 2, 3, and we have p to the 4th, or just p4. Okay, so that's just really telling you how many electrons are in that p subshell. Okay. Any questions here so far? How are we with just the general format of identifying electron configuration? Let me know in the chat if you guys have any questions with this. If not, I'm going to keep going. All right. And another type I wanted to do was iron, so something a little bit more complicated. Let's start off with iron. And this time I'm actually going to do the abbreviated method for iron. And let's see if I even have that. I don't. I'm actually going to do the expanded. I'm sorry. I'm going to do the expanded method for iron. So for iron, it is right here. All right. So starting this off, we would have started with the first row, and this would have been 1s. And yet I know that this is cut off, but this would have been helium. This would have been helium. And then that would have been 1s1 for hydrogen and 1s2 for helium. So then iron would then for sure have 1s2. Continuing on. Next, we're on our second row. This would have been 2s2. Keep going. We're then moving on to our p block. So then this would have been 2p6 because we used the entire portion of this. And then we're going to keep going. We're now in our third row. So this would have been 3s2. Continuing on. And then now we're on 3p. We use the entire row, so that means it's 3p6. And how I know this, by the way, this is really 1, 2, 3, 4, I know this is cut off 5, and then 6, there should have been another row here that would have been 6, P6. And then from there, I'm going to keep going. I'm right here on our 4th row, and we would have counted 4s2. Okay, 4s2. And then now I'm just going to count all the way up to iron. So let me remember that the D block, there's always going to be one less than the actual row that it's in. So we're going to count 1, 2, 3, 4, 5, and 6. So iron would have then been 3d to the 6th. And that would have been it. Okay, so let me see if I can, that would have been the method. And then I'm going to get into, I know it's, let me get into the abbreviated method. So the abbreviated method is really just looking at the noble gas that's right before the column that the element is actually in. And I'm going to place that in brackets, just looking at and here, let me see if I could even just write that in. So if we wanted to do iron, I know it's not drawn here. I'm going to draw it for you guys. I don't know what happened with this, but let's see. The one that's right after chlorine, the noble gas that's right after chlorine is argon. So I'm going to use argon as my noble gas or my abbreviation. I'm going to put that in brackets. And I want you to think of this as really just like a placeholder or like a bookmark. And it tells you that we're going to start from argon and then continue on from the next row. So then the next row is going to be 4s2 and then 3d6. So this is so much nicer and so much easier because this is really essentially telling you that argon replaces this entire chunk or the entire beginning of our expanded form of electron configuration. So this is the abbreviated method that we just did. You always look at the noble gas that's right before the element that you actually want. Okay. I'm going to move on to different types of ions specifically for transition metals. So doing this, there's a slight rule that we do have to know. And, oh, I had it here. Cool. Okay. So let's say if we had iron, which we really did the electron configuration, the expanded method. Now, if we added a 2+ charge on iron, so remember those charges for any sort of ion. Ion is just an element with a charge. Iron with a 2+ charge means that we're actually removing or subtracting 2 electrons because electrons are negatively charged. So looking at that too, a lot of times students think that we're just going to subtract 2 from the last part of our electron configuration. That's not the case. So since we were talking about different types of energy levels as to, which one's the strongest, which one's the weakest, S was very, very weak. And then anything after that, so D and F are going to be very strong energy levels. So we don't want to mess with that. We don't want to remove any electrons from the higher energy groups. So a rule of thumb really is you're always going to remove electrons from the lowest orbital, which is S. So in our case, we're actually going to remove our S electrons first before we even touch anything on the D orbitals. So another thing to note is electron configurations, or really just the structure, the element itself, prefers to be full or half full subshells. So like, let's say for D, it prefers to be half full, which would have been D to the 5th, or completely full, which would have been to the 10th. That just means there's 10 possible electrons in our D orbital or shell. Okay, so continuing on with this question, for the 2+ charge, I'm going to completely eliminate the S electrons or the S subshell or shell because that is the weaker one in energy. We don't want to touch that 3d6. Okay. So since we did that, this is our new electron configuration. If we were to do that again now with a 3+ charge. So yes, we eliminate the 4s2 shell again, but we still have one more to eliminate since it's a 3+ charge. So now I will subtract from that last orbital. So that would have been 3d5. And this is okay because D5 is still half full, which is stable that way. Okay. Any questions so far with electron configuration? Okay, let me know in the chat if there is. If not, that's really what electron configuration is. One more thing that I did want to mention. Let's see. Okay. Let me see one question. How would you be able to draw an orbital diagram for one excited state for CR by using the arrows? Okay. Let me see if I can get to that question, Jennifer. Okay, why don't we go ahead and actually look at that right now and answer that question. Jamie says, what if subtracting an electron doesn't leave you with 5? So that won't be the case. They won't give you something that's like a Fe4 plus, because that's just not stable with that element altogether. What I typically see is they're either going to be adding electrons or subtracting enough for the shell to be half full. Yeah, that or else it just wouldn't exist. And then let's see if I can answer Jennifer's. I know you guys are going to see my screen. Let me see. There we go. So Jennifer, I'm going to go ahead and start answering your question. So Jennifer asked, how would you be able to draw an orbital diagram for one excited state for ZR by using the arrows? Okay. Okay. I know what you're talking about, Jennifer. So let's see. Let's see what we got. All right. So this one's a little bit more complicated. Not too bad, though. So let's just locate where ZR would have been in the beginning. And ZR would have been right here. All right. So for your overall arrows, and you know what? Let's see if I can upload something. I don't even know if I did that, because that might be beneficial. Yes. Awesome. To answer this question even better. Let's give it a second. There we go. Okay. So with the arrows, all that's really talking about is you want to figure out like where to put the electrons, and then understanding how we're going to fill these orbital subshells. You might have seen some sort of diagram like this. This is really just a way to properly fill the electrons. We're also going to apply Hund's rule, as I mentioned. Hund's rule, once again, was just making the electrons kind of like not be in the same exact subshell every single time. And I'll get to that once I'm actually doing it. It makes more sense once I'm showing this. But for our ZR, let's just start off with our overall electron configuration. Let's do the expanded method. So I'm going to start off with 1s2. So everything really starts off with 1s2. All right. Then I'm going to continue, and we'll see that we'll then continue going to 2s2. I'm right here at the second shell. And then now I'm going to continue on to 2p6. Okay, so we're just going to, it's really just kind of going just straight along. All right, so I'm just going to keep going like this and back and forth. So we see what I'm doing. All right, and then now I'm going to keep going, and it's to 3s2. I'm on the third row. And then I'm going to keep going, and we're going to go to 3p6. Jennifer asked, how can you tell if it's in the ground state or excited state? Got it. Ground state means it's neutral, has no charge. Excited state means that it has some sort of charge. That's really it. Yeah. And was that the main question, Jennifer? Was it not how to fill the actual electrons with this diagram? Let me know. I'll keep going with the electron configuration just as an example either way. While you answer that. All right, so then this would have still been 3p6. Then I'm going to keep going now to the fourth row, and this would have been 4s2. And then we're going to keep going. Now this is 3d, right? We always subtract 1. So this would have been 3d10. Now we've reached 4p6. Goodness. And then we're going to keep going. Here, let me zoom in. 4p6, I just went through this whole entire route. And then now we're finally at that correct level of ZR, and this would have been 5s2. And then next it would have been, this is in 4d1, 2. So here, let's write that. So then this would have been 5s2 and 4d2. That would have been your overall electron configuration of ZR. And then how I would write this, just to show you what you would have done for the arrows, is since we had 1s2, I'm going to draw this out inside these little subshells. So those are our electrons, different spins. Let me see if I can, yeah. And then this would have been 2s2. So still drawing that out. And then we filled the 2p as well. So this is Hund's rule, where I'm just going to go 1, 2, 3, come back around, 4, 5, 6, keep going. We're still filling all of these subshells until we get to 4d. And then I'm still going to just keep filling up all of the subshells according to Hund's rule, just because that's the proper way to write it. And then now we're getting closer to what we actually had. And let's see what I'm going up to. I'm going up to 4d2. So then 4d2, I'm just going to stop. I'm going to put 1 and 2, and that's it. All right. That would have been it. So just in case you guys see that on any sort of homework question or exam, I typically see those on homework questions. And let's, oh, nope. All right. Moving on. So that was the main idea for electron configuration. Let me know if you guys have any more questions on that. I'm going to move on to net ionic, where I know that we do have a lot of questions on that. Okay, and let's start off with this first example. Okay, so for net ionic equations, they're going to start off with giving you a molecular equation. So one thing that you have to know is make sure that the equation is actually balanced. So in our case, I really went ahead and have a balanced equation. We start off with our molecular equation. For net ionic, you only are going to break apart the compounds that are aqueous into separate ions. So if I'm speaking a totally different language, let's go through that more. Okay. So let's look at these different phases that we have. So we see that we have aqueous, solid, and aqueous. Okay. So we only want to separate the aqueous compounds, but we're going to leave. So this is really important to note. We're always going to leave our solid, liquid, or gases. I don't ever see gases, but just in case, you only separate your aqueous into ions. Okay. So that's a really, really big clue and something that we for sure have to know. And then another thing is going to be your charges. So this is where polyatomic atoms come back into play, as well as naming compounds. We definitely have to remember those charges. So I'm going to start off with just doing the total ionic, or also known as the complete ionic equation. Total and complete ionic just means we're breaking all of the aqueous compounds, so all of the aqueous compounds, into totally different ions, okay? So we're separating everything apart. So I'm going to do that here. And magnesium has a charge of 2+. Okay, we should know our charges for our periodic table. So magnesium has a 2+ charge, and it is also aqueous. All right, so that's my first ion. Now, this is also telling me, the subscript 2, that I have twice as many nitrates, or NO3s, and nitrate has a minus charge. So I'm going to show this. Here, let me write the net, the total ionic here. This would have been magnesium 2+, aqueous, plus 2, because of that subscript, right? The subscript, 2 NO3 minus, still putting the phases as aqueous, plus, I'm going to keep going. So then now that I broke that one apart, I'm also going to break apart this other aqueous compound. So we have 2 sodiums. So I'm going to say 2 Na+. And then what else do we have? We only have 1 carbonate. And carbonate has a 2- charge. So let me show that. So then continuing on, and I'm going to run out of room, I realize. Let me write that over here. So I'm just separating everything into ions. accordingly. And we'll continue with this. So then bringing this down, this would have been 2Na plus CO3 2 minus. All of these are still aqueous. Okay, continue on. I'm not going to break apart the solid, so this remains. I'm not going to touch that at all. So I'm just going to rewrite that. And this remains as a solid, but we still have one more aqueous. So I'm going to break this apart. And breaking this apart, I know that this would have been 2, right? That 2 is going to actually apply to both of the Na and the NO3. So this would have been twice as many Na, so 2Na plus, and 2 NO3 nitrate minus. And I'll show that here. So 2 Na plus, that's also aqueous, plus 2 NO3s, that's also aqueous. Okay. The next step after we get this big old long equation, this is our total or complete ionic. The next step is to cancel out all of they're known as spectator ions. Spectator ions are really just like I want you to think of like terms, kind of going back to math. So the like elements or the like compounds that are on the opposite sides of the equation. So looking at this, we see the ones that are opposite from each other is going to be nitrate. So those would cancel. And then you're also going to have Na, sodium, cancel out. Okay, that's the only thing that cancels. And here I have this nicely written out. So those are the only things that are going to cancel. So those are your spectator ions. Everything that you cancel out are your spectator ions. Okay, I have a trick for you. So a lot of times students ask me, do I really have to do this every single time? Now, if you are just given the molecular equation and asked to just jump to the net ionic, no, you don't have to break everything apart. Shocking, I know. Here, let me continue with the trick. So your net ionic is always going to consist of whatever solid or liquid that you actually produced. Okay, so meaning whatever you didn't separate. So in our case, we didn't separate this solid, right? So if we didn't separate that solid, it has to have then been produced in our net ionic. Our net ionic, then what does the beginning have to be? Well, the beginning has to be whatever produced that solid or whatever produced that liquid, whatever we're forming. So how I can just instantly tell is, you could even see it in the net ionic, in the total ionic, is that our solid here has to then have been or have left carbonate and magnesium to be able to even produce that solid. Okay, so that's how I just instantly knew, looking at this. Here, I could even show you how I would just instantly see it from the very beginning, from the molecular. How I would see this is, if I know that that's our solid, then our net ionic has to produce that solid. There's no way around it. And then now if I broke apart only that solid into specific ions or different ions, we know magnesium has a 2+ charge. That would have been aqueous. And then carbonate would have been CO3, 2-. And that's, once again, just knowing your charges. And you're done. That would have been the net ionic equation. Okay. Any questions with that trick? I mean, I love that trick. I know they don't really teach you that. It's a quick way to just instantly get to your net ionic. It's another way to even check yourself and make sure that you're right, that you got your solid. So that's kind of the concept here. But the shorthand, or everything that's condensed, once we cancel out everything on either side, is the net ionic. All right. So that's how you can tell the difference. I'm going to go ahead and give you another type. This is a special type. Let's say if everything is aqueous. Trick question. If everything is aqueous, if we were to then break everything apart for our total or complete ionic, wouldn't everything be a spectator ion, so it would cancel? Yes, it would. Everything would cancel, and that would mean that no reaction occurs whatsoever. So if we don't produce a solid or a liquid or really anything, if we only have aqueous on the reactants and the product sides, that's no reaction for your net ionic equation. So in our case, you just notice this is aqueous, aqueous, everything is aqueous. Boom, you then know your net ionic is no reaction because everything cancels. All right, so I have seen that a lot, so beware of that question. Okay. I figure we try one together. So a lot of times what they're going to do is they're not going to give you the balanced or the finished molecular equation. They would first give you your reactants and say, predict the products and get to the net ionic equation. Fun stuff. So another thing that they also have you do is use a solubility table, and I'll be teaching you how to use a solubility table. Okay. So this is known as a double replacement or double displacement reaction. How I knew that was that both of these are compounds. So two compounds added together will produce two different compounds. That's a double displacement or double replacement reaction. So how I approach or figure out the products for this, I go back to foiling in math. So as you guys probably may know, I also tutor math. So I will relate a lot of these concepts back to math, just something that you've seen before. So I like to look at this as the inner with the inner and the outer with the outer. And that's what's going to combine to form completely new compounds. So recall that for any sort of ionic compound, it consists of a metal and a nonmetal. The positive goes first, right? Our metal goes first, and our nonmetal, which is negatively charged, goes last. So in our case, the aluminum would have gone first. Aluminum has a 3+ charge. You have to know those charges. And our PO4 has a 3- charge. There is no need to balance out your charges because they're really balanced. So that's our first product, aluminum phosphate. Okay, moving on. So then now I'm going to do the outer with the outer. And once again, positive first, so your metal first and your nonmetal second. And then I'll just have potassium come down as a positive charge. This subscript of 3 does not come down. The reason is because that 3 was only placed there to balance out phosphate's charge, which is typically a 3- charge. It's the only reason why that subscript was there. So as we're combining, forming new compounds, that does not continue on. Okay. So that would have been K to a positive 1 charge. And then NO3 has a minus charge. So once again, this 3 does not come down because that was only there to balance out the aluminum. Okay. So once again, those charges are then balanced. And there's nothing else to do for that but to balance out the entire equation, and then to figure out what our phases are, meaning is it soluble, is it insoluble, and we'll get to that. So this is just a method how to figure out your products given only the reactants. Okay. So now let's balance out this equation. So practice balancing equations, I'm going to write out everything that we have. So we have potassium. I'm going to leave all of the polyatomics put together because we can do that since they're the same on opposite sides. And then aluminum. And lastly, same thing goes for NO3 or nitrate. So I'm just going to write that on either side so I can balance out and just know how many of each I have. Looking at the subscript of the 3, we have 3 potassium. There is only 1 phosphate because there are no parentheses telling us there's more. Okay. Like notice there's a difference here with NO3. There is a 3 on the outside in parentheses. So there's actually going to be 3 NO3s. And then so in our case, we said PO4 would only have 1, aluminum only has 1, and the subscript told us that there was actually 3 NO3s. Now potassium has only 1, PO4 1, right? There's no parentheses. Aluminum 1, nitrate, there's no parentheses, so there's only 1. Okay, so we're going to balance out. Let's start off with potassium. And I'm going to place a 3 in front of that potassium. This then multiplies with the potassium as well as with NO3. And we now have 3 potassium and only 1 phosphate, 1 aluminum. That didn't change. And 3 NO3s. And just like that, we're balanced. Yay, I like those. Those are the nice ones that you rarely see. Okay. So the next step is to talk about solubility, and something to note that if something is soluble, that refers to it being aqueous. So this is our symbol for aqueous. And if it's insoluble, that means it's going to be a solid. Okay, so soluble, aqueous, insoluble means it's a solid. And let's go on to our solubility table. Okay. So there are endless possibilities as to what a solubility table can look like. Typically, I see this common case where we have two different like separations, where our first one tells us all of the ions that are soluble versus the second one that tells us everything that is insoluble. Okay, so there's one column that's like it's soluble, and there's another column that says it's insoluble, and they always tell us the exceptions to that rule. All right, so how we use this, I'm going to bring back and just rewrite what we had for our overall products, just so it's easier to tell. So our products we saw were aluminum phosphate, and we had potassium nitrate. Okay, so how we refer back to this table is I'm going to start with potassium nitrate, and we always start with the ending or the non-metal. Okay, so I'm going to look for NO3, which is nitrate, and I find that here, and I see that this ion is typically always soluble. So are there any exceptions? No. So exceptions to the rule, if it does fit that rule that it is an exception, it just means that it's then insoluble. So it's always opposite from whatever column it would have been. So in our case, we don't have that. Nitrates are always going to be soluble, meaning this is going to be aqueous. Okay. Now I'm going to go on to aluminum phosphate, and PO4 phosphate is in the insoluble column. So these are the ions that are typically insoluble. And I'm going to look at the exception and make sure that my aluminum doesn't fall under that exception. Okay. So really the first column, the ions that form insoluble compounds, that typically just refers to the nonmetal or the ending or the last part of your compound. And then the exceptions to that rule are talking about your metal or the beginning portion of your compound. Okay, so this is really talking about our end, and this is our beginning, or I'm just going to say beginning portion of it. Okay, so aluminum is not within, it's not going to be in our first column. It is not ammonium. It's not NH4. So right then and there, I know, yes, phosphate, aluminum phosphate will be insoluble, making it a solid. So that's helpful because we know we only separate the aqueous solutions. So this is solid, this is aqueous. Okay. Continuing on. Now we're going to get into, so it's balanced, everything has its phases. I'm going to jump into the total ionic equation, and then we'll get to the net ionic equation. So let's break apart everything that has an aqueous. So our aqueous will be the first one. So I'm going to separate this into 3 K pluses because of this subscript, and it's going to be aqueous. Then plus. Now I'm going to separate this into PO4 with a 3 minus charge, aqueous. So I'm just separating every individual ion. And the next one's going to be aluminum with a 3 plus charge. That's aqueous. And then plus, I'm going to do, now we have 3, right? This subscript right here, 3 NO3s with a minus charge, aqueous. I'm going to leave that solid alone, so that doesn't change. So aluminum phosphate, it's a solid. And then now going back to this one, this 3 gets distributed to both. So there are 3 potassiums and there are 3 NO3s minus. So I'll write that here. So plus 3 potassiums plus 3 NO3 minuses. Oh, running out of room. Okay, and those were aqueous. So that would have been our total or our complete ionic equation. And now we'll just cancel all of our spectator ions, and that'll then give us our net ionic equation. So in our case, we're going to have everything that doesn't build or form that solid. So our potassium will cancel. Our NO3s will cancel, and that's it. Because we wanted to form this solid. And what are the reactants that have to make that solid? The aluminum and the phosphate. So I could have instantly just gone back, right? My trick. If I just wanted the net ionic equation, after balancing all this and figuring out the phases, I would then go back and see which one formed a solid. And how I can just look at this is if I know what my solid then is. So if I know that this for sure was this is my solid, then I would just break these two apart. and that would be my net ionic. I could just instantly jump to that. So aluminum would have been aluminum with a 3+ charge, and that's aqueous. Phosphate has a 3- charge. That's aqueous. I'm done. That's the net ionic equation. Okay, so use that trick if you will. If they do ask for a total or complete ionic equation, yes, you do have to break everything apart. So I've seen just several different questions if they only ask for the net ionic. I used to do that. When I figured that trick out, it just saved me so much time. So cool. All right. So moving on. Any questions with net ionic equations? Let me know. If not, I'm going to move on and just practice a bunch of stoichiometry. Okay. So I'm moving on to stoichiometry. I know everyone was saying that this was something that was really difficult for them. And then I realized for next Sunday, I definitely want to know what you guys are on. So I think I'm just going to keep doing this just to get your feedback and to know, because I know everyone's on different sections. So let me know in the chat if there's a specific topic that you want me to go over, so I can talk about that next Sunday. I'm just really trying to, have this benefit you guys as much as possible. So I want this to kind of be like the same place that you guys are on now in class. So let me know. All right, so moving on to more stoichiometry. This first question states, what mass of sodium iodine will react with 7.82 grams of chlorine? And they give us an unbalanced equation. So we'll practice our balancing. That will be our first step here. So before we even begin, I'm just going to balance out this equation. And I'm going to write out what we have. So we have sodium, iodine, and chlorine. Sodium, iodine, and chlorine. And just writing what we have. So we only have 1 sodium, 1 iodine, and 2 chlorine. We have 1 sodium and 2 iodine and 1 chlorine. So since there is no hydrogen or oxygen, those we typically leave to the end, I'm just going to start off with let's see, iodine. Why not? So I'll place a 2 in front of that sodium iodine and iodide. And then this would have been 2 now, sodium and 2 iodine. And we still have that 2 chlorine remaining. And then now I'm going to balance out the other side. And we need 2 more of our Na and 2 more of our Cl. So I'm just going to put a 2 in front and we're balanced. Everything else is fine, right? This 2 distributes on to the Na and the Cl, so that's fine. That one was nice. And then now I'm going to get back to the actual question for stoichiometry, and we'll get to there. So always identifying your given and what you're finding. We'll start there. So our given in this question is 7.82 grams of chlorine. Okay, so Cl2. And then now they're telling us to find the overall mass is measured in grams. So grams of NaI. Okay, so that's what we're doing. And then now let's develop a plan to figure out how in the world we're going to do this. So starting off with, here's our plan. Starting off with the units of your given, we have grams of Cl2. Now I want to make a big note here, how I just instantly know to go to my next step. Whenever we are changing the compound altogether, you have to do a mole-to-mole ratio. And that's why we were actually given the equation and having to balance it out. So you do a mole-to-mole ratio whenever you have a balanced equation, and specifically whenever you are changing the compound. Okay, change compound, mole-to-mole ratio. So in our case, I'm now going to get to moles of chlorine. Once I do that, I can then do a mole-to-mole ratio to change the compound altogether to NaI. And lastly, I can go from moles to grams to NaI. And we'll write out every single step in between, all the different conversion factors that you will be using. So going from grams to moles is molar mass. So molar mass of chlorine or Cl2. Just remember that how I knew that was just molar mass instantly was molar mass has the units of grams per mole, right? Grams per mole. That's going to act as our conversion factor or a way to get from grams to moles or vice versa, moles to grams. All right. So then moving on, The next conversion factor would have then been mole to mole. So that's our mole to mole ratio. And we find that using the balance equation. And what I mean by that, it's just the coefficients or numbers in front. This is 1, 2, and 1. And we'll get back to that. Then lastly, now going from moles to grams, molar mass again, right? Whenever we're going grams to moles or moles to grams, that's going to be molar mass. And this specifically is now the molar mass of NaI. All right, let's set it up. So setting this up, starting off with your given, that's 7.82 grams of Cl2. And aligning the units across from each other. So I'm going to place the grams across from our initial unit. All right, now we need to figure out the mass of chlorine. So since there are 2 chlorine, there would have been, right, there's 2 chlorine. So this would have been 2 times the individual mass of chlorine, which would have been 35.45. Those 2 multiplied would then give us 70.90. And then this would have been on the bottom. Some of these I actually just have memorized. I've been doing this for so long. So yeah, some of these I do have a little bit. You probably saw me do that really quickly. I have some of these memorized. You'll get to that speed after you've seen so many of these. And then from there, this is just the molar mass. So remember, molar mass is grams per mole. So then grams is on the bottom to cancel out, and we have per 1 mole of Cl2. Okay, so grams specifically for molar mass, the actual like addition and everything that you're taking from the periodic table, that is always going to go with grams, and it's always going to be 1 mole. All right, for molar mass, always 1 mole. Okay, so that was our first conversion factor. Moving on. Now with our second conversion factor, so after we cancel out the grams and grams, we now have moles of Cl2. We have to change the compound. So this is going to our second step right here, where we then are going to do a mole to mole ratio. And I'm going to put the same units on the bottom as aligning them across from each other. So this would have been moles of Cl2. And on top would have been moles of NaI. That's what we're solving for, right? We want that compound specifically. So I'm going to go back to my balance equation. And we're going to see how many moles of Cl2 and how many moles of NaI do we have. So looking back at our balanced equation, we have 2 moles of sodium iodide, and we have 1 mole of Cl2. So that's what I'm going to put. So that's where I'm taking those numbers whenever I do a mole to mole ratio. You pull them from the balanced equation. So we said we have 2 moles of NaI and then 1 mole of chlorine. Not done yet. So then next, those moles and moles of chlorine would cancel. Last step. We'll now get to the molar mass of NaI because we're trying to find the grams. So moles of NaI will go on the bottom per every gram of NaI. And now we have to figure out the molar mass of NaI. And then Na and I, we're going to do everything separately. So Na or sodium has typically a mass of 23. And then iodine has 126.9. And then we'll add this up. So then this would have been 149.9. So 149 on top, 0.9 per every 1 mole. And then we'll multiply straight across and divide. Any questions with the setup? Any questions with this specific type? Let me know. I'll clarify. And let's see what this would have given us. So multiplying straight across, that's 7.82 times 2 times 149.9 and divide by 70.9. And we get 33.066 grams of NaI. But do we leave it like that? No, right? Sig figs. Those sig figs always come back. So I'm going to go back to my initial question and I look at my given. Your given has 3 sig figs. So we have to round to 3 sig figs. So going back to our question, rounding to 3 sig figs, we'll stop right here. So we will round up. Our final answer would have been 33.1 grams of NaI. And that's it. Okay, we're going to do another one. And let's see what we do with this. So erasing everything, let me just get to. All right. One more question on stoichiometry. Okay. And as mentioned before, let me know in the chat if you guys, what you want me to talk about next Sunday. If there's a specific topic, I just want to know what you guys are on so I can help you as much as possible. Okay. So this last question on stoichiometry says, how many molecules of oxygen are required to react with 174 grams of carbon monoxide? All right. So first step, balance our equation. And I do have another question. Let's see. I got a question saying, so the molar mass is determined by the subscript on Cl, not from the coefficient. Correct. So the Cl, and let me go back to that. So if we were finding the molar mass specifically of just chlorine, yes, the subscript tells us how many chlorine specifically we have. So it doesn't come from like if we had a number here or like this was 1. We said that this was the case. So it does not come from the coefficient in front. That coefficient in front is for our mole to mole ratio. The subscript then tells us the molar mass. So this is telling us that for chlorine, we have twice as many chlorine or twice the amount of one individual mass of chlorine. Okay. Just to answer up that question. And then now let's go back to our next one. So I'm just going to balance this out. Balancing out this question, we really only have carbon and oxygen. So not too bad so far. And then we have 1 carbon. We actually have 3 oxygen. There's 1 here plus this 2. So 3 oxygen. And then next 1 carbon and 2 oxygen on the other side. So balancing this out, the only thing that's unbalanced is going to be our oxygen. So this could be a little bit tricky because there's an odd amount of oxygen on our reactant side. So let's see what we can do. Now, what I like to try is I like to think of kind of like a common denominator or a common factor that they both share. So in our case, we can make it into 4 oxygen. And how I would do that, since we already have 2 here, what if I were to put a 2 in front of carbon monoxide? Then that would then double our carbon, and we now have 4, right? This 2 plus this other 2 gives us 4 oxygen. And then now I can balance out the carbon on the other side. So this would have been 2. This is essentially distributing. So our carbon would have been 2, and then 2 times that 2 would have been 4. We're balanced. Okay. So continuing on with this question, I'm going to start off with just what we're given and what we're finding. So our given is that 174 grams of carbon monoxide, or CO. And you're finding how many molecules? Molecules. Not moles, not grams, molecules of oxygen, which would have been O2. Because it's already balanced out, and that's what they mean by oxygen. They mean O2. So, okay, let's develop a plan. Our plan, always starting with our given unit, which was the grams of carbon monoxide. So let's just identify what's going on, right? We have carbon monoxide changing the compound, right, to O2. When we change the compound, we have to use a mole to mole ratio. And that's where these coefficients come in with our mole to mole ratio. So that's going to be one thing that we have to do, right? So that's actually the first step I'm going to be. I'm going to change everything to moles. So going from grams of carbon monoxide to moles of carbon monoxide. And by the way, if you ever feel like, I never know where to start, I never know, what to change it to, big hint, everything ends up equaling moles somehow, some way. So it's actually a safe way to start. Like if you were to start from molecules and you're trying to get to grams, or vice versa, you'd then change molecules to moles and then get to grams. Like everything equals moles. So that's a way to get to pretty much any sort of unit for stoichiometry. So that's how I just instantly knew to get to moles for this step. So I went from grams to carbon monoxide to moles of carbon monoxide. Now I want to change my compound. So I'm going to do a mole to mole ratio and get to O2. Next step, anytime you see Molecules, particles, atoms, formula units, you have to use Avogadro's number. So we have moles of O2, and we're going to use Avogadro's number to get to molecules of O2. So let's just distinguish what we're going to be using throughout everything. So starting off with our grams to moles, our first conversion factor has to be molar mass, specifically of that carbon monoxide. Now going from mole to moles, and we're changing the compound, we're using that mole to mole ratio, just using the balanced equation. And then now moles to molecules, keyword molecules, that is Avogadro's number. All right, let's set it up. So setting this up, starting off with your given, that 174 grams of carbon monoxide, aligning those units across from each other. So I know to put grams of carbon monoxide on the bottom. Now we have to figure out what our molar mass is of carbon monoxide. There's only one carbon and one oxygen. So I know carbon has, it's roughly 12.01, and then oxygen is 16.00. Adding those two together gives us 28.01. So 28.01, and molar mass is always per every 1 mole of carbon monoxide. That was our first conversion factor, right? This molar mass. Now I'm going to move on. And we see that our grams and our grams of carbon monoxide cancel. We're now at moles of carbon monoxide. I'm going to align those moles across from each other. And I'm at the second conversion factor, that mole to mole ratio. So looking back, I'm going to go to moles of O2. I'm going to look back at our balanced equation and compare our moles of carbon monoxide and moles of O2. This is where we look at those coefficients in front. So our moles of carbon monoxide, we have 2 moles of carbon monoxide per every 1 mole of O2. So that's what I'm going to put back here. We have 2 moles of carbon monoxide per every 1 mole of O2. Not done yet. So now I'm going to cancel out those moles of CO. And now we're finally at moles of O2. And our last step, Avogadro's number. So we're going to plug in, let's see, we're going to put those moles of O2 on the bottom. That's per every 1 mole of 6.022 times 10 to the 23rd. You can't have the guacamole without the avocado. Yes, you saw that video. So if you haven't, do yourself a favor and check out that video, because for the sake of comedy, I got guacamole smeared on my face. That was great. Great facial cream. So now looking at this, this would have been Avogadro's number on top, molecules on top of O2. And that's it. We'd multiply straight across. So multiplying 174 times the Avogadro's number. And then also, I've seen this before where students don't necessarily know how to do this. So I want you to think that we're multiplying straight across. So let me just show you that what you would do there. 174 times 6.022 times 10 to the 23rd. That would have roughly been 1.04 times 10 to the 26th. And then I'm just multiply these two straight across. And then I'm going to divide by 28.01 times 2. To avoid any calculator errors, you can separate it apart. And then now I'm going to divide those two. So just make sure that you for sure multiply these out. And then let's see what we get. 26 divided by 56.02. And this gives us 1.856 times 10 to the 26th. And that's molecules. So I'm going to round to the appropriate amount of significant figures. So back to the question. Let's look back at our given. We had 1, 2, 3 significant figures. So I'm going to round to 3 sig figs. So let's go back. 3 sig figs. So right here, I'm going to round this up. This actually would have been 1.86 times 10 to the 26th molecules of O2. And that's it. All right. So definitely let me know. Let's see. Let me see if I have any questions so far. Let's see. Let me make sure I don't have any other questions. Okay. People are leaving their suggestions. Great. Yeah, definitely leave your suggestions. Let me know what you want me to teach for next Sunday. And for those of you joining us a little bit late, I just wanted to mention something that I'm doing for my subscribers specifically. So as I mentioned before, I typically charge for tutoring, between 40 to 60 hours. This is my profession. But since you are a subscriber, I'm doing this completely for free because I just appreciate you guys so much. And something else that I'm doing really exciting is if you help me get to 10,000 subscribers, I will do an 8-hour live tutoring session to prepare you for finals. I know. I'm ready for it too. So definitely share, please share with my videos, let your friends, classmates, your teachers, anyone that you just know will benefit from these tutoring sessions and just my videos in general. Please get the word out. And like I said, I will do an 8-hour live tutoring session where you just ask me questions. We go over, we really just knock everything out and prepare for your final. So definitely spread the word, and I'll be happy to do that for you guys. So also reserve your spot for next time. And I will be contacting those of you who fill out the form that you find in the description box below and everything for my videos. And I'll see you next Sunday. All right. See you guys.